This is lecture 5, where we'll talk about the properties of the Fourier transform. So, last week in lecture 4, we spoke about the Fourier transform, and it was a continuation from our introduction to spectral analysis when we spoke about the Fourier series in week 3. So the Fourier series was how to represent a periodic signal in the frequency domain. We then introduced the Fourier transform, which allowed us to represent an arbitrary signal, so not necessarily a periodic signal. Any signal can be represented in the frequency domain using the Fourier transform. Now, in this lecture, we'll look a little bit more closely at the Fourier transform and introduce some of the properties of the Fourier transform that make it easier to use, and it allows us to use it in different scenarios. So if you like, lecture 5 is not a full lecture, it's a top-up lecture for lecture 4. So we're almost halfway through the 11 lecture sequence, and it's the penultimate lecture in the signals section. So this section here, this is where we talk about signals, and starting from week 6, we'll be looking at systems. So just a quick reminder of the schedule. This is where we are now. We are at lecture 5. Next week, you'll have a test that covers the contents of lectures 4 and 5. So these two topics, the Fourier transform and the properties of the Fourier transform, are included in your class test on the 16th of November. So make a note of that. So a quick recap. In lecture 4, we introduced the Fourier transform and the inverse Fourier transform. So these were two transformations represented by two integrals. One of them, the Fourier transform, would take a time domain signal and represent it in the frequency domain. In the inverse Fourier transform would take that same signal in the frequency domain and represent it in the time domain. So for the Fourier transform, we take f of t, we multiply it by this complex exponential and integrate it over all time. And remember, because it's not a periodic signal, we're not integrating from minus t over 2 to t over 2. We're not dividing by t, it's over all time. So the two main differences between these integrals are the minus sign for the Fourier transform and the lack of minus sign in the inverse Fourier transform, and the 2 pi factor. The 2 pi factor comes about because we're not using frequency in hertz, we're not using f, we're using omega, which is equal to 2 pi times f. We also introduced this idea of Fourier transform pairs. So we said some signals in the time domain, or all signals in the time domain, have corresponding spectra, and together we call these Fourier transform pairs, and some of these pairs we need to know. And we introduced the idea of filters, and we said the basic filters are a low pass filter, band pass filter, high pass filter, and band stop filter or notch filters. And we introduced what ideal versions of these look like, and we looked at problem sheet 4 together. And there's a whole collection of pencasts to support the questions in problem sheet 4. So before we start talking about the properties of the Fourier transform, I want to just say a few words about why the Fourier transform actually matters and where we might encounter it. So today we're talking about the properties of the Fourier transform. Two properties of the Fourier transform which often are represented separately are the Convolution Theorem and Parseval's theorem. Both of these are properties of the Fourier transform, but are sometimes mentioned separately, so I've identified them as separate points. So this week you'll also have problem sheet 5 with a very large collection of pencasts to support it, and you'll have a practice test for class test 3. So this practice test goes online on Tuesday night. The practice test will be available all the way until Monday morning. Monday morning it goes offline because that's when your class test 3 goes online. So again, my weekly reminder that if you really want to do well at the class test, you need to spend some time on the practice test. Okay, and don't attempt the practice test until you've done the problem sheet, and don't attempt the problem sheet until you've understood the lecture. So that's the order, basically. So a few words about where we might come across this. So the Fourier transform, we might not use that word we might just call it spectral analysis, we might just call it frequency domain, but you'll come across it in the field of image processing. Image processing is anywhere where you have an image and something is done to the image. So this process here is simply image enhancement. Something is done to make an image look better. But sometimes an image is processed for some purpose. So for example, here, iris recognition, we can process this image here, and by taking a Fourier transform of this image here, of the iris, we can use that for recognition purposes. The same with fingerprint analysis. In astrophysics and geophysics, there's a lot of image analysis, and often this is done in the frequency domain. Again, in voice recognition, this is often done in the frequency domain. So even though we think of signals as being in the time domain, often one- and two-dimensional signals are represented more meaningfully in the frequency domain. So for example, for voice recognition, here what's being shown is a frequency domain representation. So the horizontal axis here is frequency. And we have some different vocalizations, different sounds. You have the ah, e, and oo. And these sounds look very different when you plot the spectrum. So look at this. The ah has a peak at around 750 hertz, another peak just above 1,000 hertz, and a peak at 2,500 hertz. Whereas if you look at something like E, the word heed, your peak is a much lower frequency. It's less than 500, and then you have a peak here closer to 2,000. And both of these are in contrast to the oo sound. So next time you speak to one of your home assistants and it recognizes your voice, it's not necessarily looking at the time domain signal, which is, in the time domain, your signal might look like that and would look very similar, whether it's one word or the other. But what's actually happening very often is a frequency domain analysis. So therefore, some kind of Fourier transform is happening. Now, if you have a two-dimensional signal, and remember we said images are two-dimensional signals, we can use that for character recognition. In this case, handwritten character recognition. So here you've got some English letters, some Arabic letters, and I'm guessing these are Chinese characters. I don't know for certain. But these will have very different frequency domain representations, and often a machine learning algorithm or a neural network or some kind of artificial intelligence might be able to recognize the differences between these easier than it can by looking at the spatial representation. So just some more examples in case you end up doing a project in your second year or third year that involves image processing, fingerprint recognition. So this is what something might look like in a spatial domain, but in the frequency domain, it's a very different representation. Again, this is a little video that I would have presented if we were in class, and this particular video is about somebody who developed a smartphone app that can take a video of somebody's face, and by looking at that video and looking at the movement of the person's shoulders, can actually extract the heart rate and the breath rate. And I'd mentioned that that could be a project that you can work on. So in your final year, you could develop a little app that can do that. And finally, applications such as enhancement of images for medical purposes, for example, are often done using the frequency domain. So any kind of filtering will by necessity happen in the frequency domain. So if it's a low pass filter or a high pass filter, all of these filters happen in the frequency domain. So that was just a little introduction to why this matters and where you might come across it. But actually, what we're actually doing is the Fourier transform from lecture 4. So I'm not going to add anything to that. That is what it is, the Fourier transform. Thank you, Joseph Fourier. That's what it is. What we're going to talk about today are some properties of the Fourier transform that make it easier for us to apply. So we'll be looking at the symmetry property, the duality property. We'll be looking at linearity, scaling, time and frequency shifting, and these two properties which have names of their own, Parseval's theorem and the convolution theorem. So I'll go through each of these. I'll explain what it is. I'll give a very basic proof and a simple comment on how we should understand this, i.e. an interpretation of what it actually means for us. Now, for this to actually be helpful, what you'll need to do is go through the problem sheets. So the problem sheets, that's where all of these come to life. This is where you'll actually be applying it. So in this lecture, I've kept the examples to a minimum, but the problem sheet is packed full of examples and questions. And the Pencast page has literally dozens of solved examples where I go through this in much more detail. So the first property is the symmetry property, formerly known as the duality property. And in simple English, what it says is that if you have a Fourier pair, that means if you have some signal in the time domain that corresponds to some signal in the frequency domain, then if you had that same signal in the time domain, its spectrum would look very similar in the frequency domain. Okay, there is a tiny factor of 2 pi, and then there's a reversal here, but in this case, because it's symmetric, it doesn't make a difference. So for example, if you have a rectangular pulse in the time domain, its spectrum looks like a sinc function. So if we had a signal in the time domain that was also a sinc function, what would the spectrum look like? Well, using duality, we know it will look like a rectangular pulse. Now, we don't call that a rectangular pulse anymore because it's in the frequency domain. We call this a low-pass filter. Why is it a low-pass filter? Because it allows low frequencies to pass and it blocks high frequencies. So if we were to multiply our signal by this, we'd be multiplying by 0 for high frequencies and multiplying by something that was non-zero for low frequencies. So this would be a low-pass filter. Now, the negative frequency axis doesn't have a real interpretation. It doesn't have a meaning in the real world, but mathematically it's necessary. Just like the negative time axis is only meaningful if we have a non-causal signal. But for a causal signal, time starts at 0. So for a signal where we have negative time, we're we're talking about non-causal signals. So that's the duality property illustrated mathematically, a little bit more detail because I'm going to introduce this factor of 2 pi and the negative omega. So this is an example, it's not a proof. If you take a Dirac function, a unit impulse, and you find the Fourier transform of that Dirac pulse, we've gone through this in problem sheet 1, but that gives you 1. Okay, that's not DC, that's constant frequency or constant amplitude for all frequencies. This is what white noise might look like. Why is that the case? Well, let's look at the Fourier integral. It's just f of t multiplied by e to the minus I omega t. So this is your f of t, and this is I omega t. And you integrate that over all time. Now, if we use the sifting property, t equals 0, replace that in there, e to the power 0 is 1. So we use the sifting property of the Dirac function to find this. Now that's not what this slide is about. What I'm trying to say is that because this gives you this, because an impulse will give you a signal with a uniform frequency distribution, then the opposite is also true. If we have something like that in the time domain, i.e. dc, then the Fourier transform of that will look like that. It will look like an impulse. So what's an impulse in frequency? An impulse in frequency, so this is where the 2 pi comes in and the minus omega, but an impulse in frequency, in this case there's a 0 here, so this is just the same as the Fourier transform A naught. So this is basically DC. This is what DC looks like in the time domain. This is what DC looks like in the frequency domain. But what I'm trying to say here is that when you have a signal in the time domain with a corresponding spectrum in the frequency domain, then if you have that same shaped spectrum in the time domain, you should expect the signal to look the same in the frequency domain, with the difference of a factor of 2 pi and a reflection in the frequency axis. Okay? Now, actually carrying out this integration isn't easy, and I've left it as a question for you here. Can you do that without using duality? If you struggle, then you will appreciate why the duality property is so helpful, because otherwise we wouldn't be able to do this. But now we have the duality property, we're able to use this. So actually coming to this, proving this wouldn't have been easy if we didn't have the duality property. Okay, so that's the first of the properties we want to look at today. Quick example, or quick question for you. So if this was in class, it would have been a question I'd ask you all to answer. But here the question is, this time domain signal and this spectrum, they form a Fourier pair. That means that the Fourier transform of this signal is equal to that signal. The question is, if we had a time domain signal that looked like this, what would the spectrum look like? So just to make this slightly clearer, e to the minus at, that looks like that. 2a of a squared plus omega squared, that might look something like that. So if we had a time domain signal that looked like that, what would the spectrum in the frequency domain look like? Well, you won't be surprised that if you see that in the time domain, then you'd expect that in the frequency domain. The only difference is there should be a factor of 2 pi. So what we want is a factor of 2 pi. So it'll either be this or this. So it should be 2 pi e to the minus a omega, because it's now a spectrum, so it won't be that, and it won't be that, because those are in the time domain. It'll be 2 pi minus b. This, strictly speaking, should be minus omega, but because we have the absolute value, it doesn't matter. So that's your answer. The next property we're looking at is something called linearity. And if you like, linearity is a combination of two other properties, superposition and homogeneity. And we'll look at that more closely when we look at systems. But for now, let's think of linearity as allowing linear combination of signals. So let's say you had a signal f of t and another signal g. So f and g. If you were to add f and g, what would the corresponding frequency domain representation be? So f of t corresponds to f of omega, and g of t corresponds to g of omega. So if I were to add the two, linearity means that the spectra would be added together. So f of t would be f of omega, g of t gives you g of omega, and if you add these two, the spectrum will be the sum of the spectra. And if you add these with weightings, so you have A times F plus B times G, then the spectra will also have the same weightings, A and B. So expressed in English, the Fourier transform, that's a Fourier transform, of a linear combination, that's your linear combination of signals, is the same as the linear combination of the Fourier transforms. Here we have a linear combination of the Fourier transforms. So it's pretty straightforward. You can prove it easily. And as an illustration, let's say f of t looked like that, some rectangular pulse. G of t is also a rectangular pulse. Each of these has their corresponding spectra. If I were to add f and g, it would give me a signal that looked like that. The spectrum I could find by simply adding the two spectra together. So the spectrum of f plus g is f of omega plus g of omega. So pretty straightforward and intuitive. Next property, a little bit more difficult. I'm going to give you a brief proof of this scaling property. And basically what we're saying is if we have a signal f in the frequency and time domain, so f of t gives you f of omega, and just to remind you, this is the Fourier transform integral. The question is, what would happen if I were to multiply the independent variable t by some constant a? So I'm not saying a multiplied by f of t, because we've done that. That was linearity. Now we're talking about f of at. So we're multiplying the independent variable. So what we're doing effectively is scaling our signal in time. So our signal in time domain might look like that. Now we're making it look like that. Okay, our signal might have looked like that. Now it's looking like that. So we're scaling in the time domain. We're multiplying the independent variable t by some constant a. What will the effect be in the frequency domain? How will f of omega be affected by that change there? So we can simply write f of at and write the definition of the Fourier transform. This, as you can see, is the same as that. So if you write the definition of the Fourier transform, this is my signal, and this is e to the minus I omega t. So this is the same as that. That's part of the Fourier transform definition. So how would we get rid of that a? Well, one way is to rewrite at as some other variable, u. And that way, instead of having f of at, you now have f of u. And then you can say, well, that means that t equals u over a. And that goes there. And then you have dt becomes du over a. So if you take that constant outside the integral, you can now rewrite this as the Fourier transform of, because look at this, this now looks like a Fourier transform, except it's scaled, and you have this factor of a in the denominator. So it's as if a time domain signal, f of at, now has a spectrum that's scaled by a factor of 1 over a in amplitude, but it's scaled by a factor of 1 over a in the frequency axis as well. So it's scaled both in amplitude and in the frequency axis. So what does that actually mean? So let's think of our pulse. Remember I said if I take a pulse and then I scale it by a factor of a, in this case a would be less than 1, what would that do? What would these two factors here actually do to the shape of that spectrum? So think about that and consider the next slide. It means that the shorter the pulse, the broader the spectrum. Why do we say that? Remember we said f of at, that gives you 1 over a f of omega over a. So when you multiply by t, you multiply by a here, let's say a was greater than 1, that would make your pulse narrower. And the spectrum would be f of omega over a. So here we're dividing by a, so it has the opposite effect. So when we squash or compress in the time axis, we're actually stretching in the frequency axis, and we're also scaling down in the amplitude. And the opposite is true. As we stretch in the time, we compress in frequency. And that sort of makes sense, doesn't it? The shorter pulse has a broader spectrum. So if you think about communication, and I'm slightly biased towards communication because I teach that in the second semester, but the implication for communication is if you have faster communication, that means you're going to have shorter pulses. That means your pulses are going to be shorter in duration. That means your spectra are going to be larger. That means you're going to be using more bandwidth. Okay, you're going to be using more frequency. So if bandwidth comes at a cost, that means it'll be more expensive. It means your channel will have to provide a larger bandwidth. So if bandwidth is limited, that means the pulse of your the width of your pulse will be limited, i.e. How narrow you can make your pulses then reaches a limit. So the scaling property, the important thing to understand is that as your signal becomes narrower, the spectrum becomes broader, and vice versa. The next property, so we're almost halfway through now, the next property is called the time shifting property. So if you have some signal, again, same scenario, some signal in the time domain with its corresponding signal or spectrum in the frequency domain, determined by the Fourier transform integral, The question this time is not if we were to multiply t by some constant a, but if we were to subtract or add some constant a, i.e. if we were to shift our signal. So you have a signal and you shift it to the right or to the left. If you were to shift your signal in time, that's why it's called a time shifting property, what effect would that have on the spectrum? Would the spectrum be shifted, or would something else happen? So again, very basic proof. Let's simply rewrite this Fourier transform, but this time using t minus a. So f of t minus a with the same e to the minus I omega t. And we'll use the same trick. We'll say, well, if we were to replace t minus a with u, we can now rewrite that. Du and dt are the same. So we've now rewritten this. And I can now split this exponent into minus I omega u and minus I omega a. And because we're integrating over u, it means we can take I omega a outside of the integration because it's a constant. Now, that gives us this, which if you look closely, this is exactly how a Fourier transform will look. So all of this is simply the Fourier transform of f of t, i.e. f of omega. So that is simply that. So what's been the effect of this time shift? The effect has been this multiplier here. So this is what we call a phase shift. It's being multiplied by a complex exponential, e to the minus I omega a. So that's cosine omega a minus I sine omega a. Okay, so this is the time shifting property. If you shift in time, the spectrum shape is unchanged. It's just multiplied by this complex exponential. So it's a linear phase shift in frequency. So the shape of the spectrum is unchanged. Let's take an example. Say you have a simple cosine. Okay, so this is a cosine that occupies the entire time axis from minus infinity all the way to t equals infinity. So it's a never-ending cosine. What's the Fourier transform of the cosine? Well, it's simply the cosine multiplied by e to the minus I omega t. This exp, that's just another way of saying e. So f of t, e to the minus I omega t, integrated over all time. So if you replace the cosine with the Euler definition of cosine, remember cosine x is simply half e to the ix plus e to the minus ix, and sine x is 1 over 2I e to the ix minus e to the minus ix. Okay, so that's your cosine. Now if you simply multiply these, that allows you to add the exponents. So you end up with two terms, a difference and a sum. And thinking back, remember we said the Fourier transform of an impulse is simply constant. So you can think of this as 1 times that. So you can visualize this as the Fourier transform of that. So the Fourier transform of an impulse is simply a constant. And using the sifting property, you'd replace omega equals omega naught. So I'll leave this step here, which isn't immediately obvious. I'll leave that for you to think about. But the result is almost what we would expect from a cosine. You would expect a cosine to have a single component, what we would refer to as the fundamental, remember? Here, it looks like there are two, but it's the same. It's just one in the positive frequency axis and one in the negative frequency axis. So this is the Fourier transform of a cosine. And that will be useful in talking about the next property, which is the frequency shifting property. Okay, we also refer to this as the modulation property, and this might be clearer next year when you look at communications in Elect 202. So for now, let's look at it as a shifting property, or a frequency shifting property. So the question this time is, if we take a signal f of t and we multiply it by a cosine, we just looked at the example of a cosine. If I multiply by a cosine, what effect will that have on the frequency domain representation? And again, if you replace cosine with the Euler definition, we now have f of t multiplied by cosine. We can now find the Fourier transform by integrating that signal multiplied by the cosine. These are all the same. Multiplied by e to the minus I omega t. This comes about because of the Fourier transform. This is part of the definition. So you've got your three components, your signal f of t, your cosine, and e to the minus I omega t, which is part of your definition. So we can get rid of that constant, take it outside of the integration. F of t, let's just leave that there. We don't need a change of variable. And we can multiply that out and add the exponents. And that gives us two integrations. And each of these actually just look like Fourier transforms. Okay, so again with a change of variable, this is actually what it gives you is two versions of the spectra of the same spectrum, each shifted by omega naught radians per second to the left and to the right. So just to illustrate that, let's look at a signal such as this. So you've got some pulse. It doesn't really matter what the equation is. You have some pulse. F of t equals e to the minus t squared. And the spectrum looks very similar. If I were to multiply that by a cosine, so you're multiplying by a cosine, that product gives you this modulated cosine. Okay, so that's not the question. That's not really what we're looking at. This is, if you like, what's happening in the time domain. This is what it looks like when you multiply something by a cosine. The question is, how does the spectrum change? What happens? And this is what happens. If this was my original spectrum, then by multiplying by a cosine, what I've done is I've created two versions of the spectrum. One shifted to the right, and one shifted to the left by omega radians per second. So that's what the frequency shifting property actually does. So by multiplying by a cosine, your spectrum is split into two and shifted to the right and to the left. That might be clearer once we start looking at convolution. You can then visualize it as a convolution with the spectrum of the cosine signal. But for now, think of it the way it's being presented. After we've looked at the convolution theorem, this might make a little bit more sense. Two more properties to go through. One of them is called Parseval's theorem, which is a property relating to energy, and one of them is called the convolution theorem, and we've sort of introduced that at the end of lecture 4. So, Parseval's theorem relates to energy signals. Remember energy signals? Energy signals are signals with finite energy. Okay, so a signal like a cosine or a sine with an infinite energy, that doesn't apply. We're talking only about signals with finite energy. And basically, what Parseval said is that you can measure the energy of a signal in the time domain or in the frequency domain, and it'll be exactly the same. So the energy of a signal is the integral of the signal squared over all time. And it's exactly the same in the frequency domain. You take the spectrum or the signal as a function of frequency, you square it and integrate it over all frequency, and it'll give you exactly the same energy. Now, because we're using omega rather than f, we have this factor of 2 pi, but this is the energy in the frequency domain. The energy includes the factor of 2 pi. Okay? In some books, if they were to use f, they wouldn't use that factor of 2 pi, but the most common representation is in terms of frequency omega in radians per second, and we do have this factor of 2 pi. So what's the energy of a signal in the time domain? Well, it's the integral of the signal squared. What's the energy of a signal in the frequency domain? It's the integral of the frequency domain of the signal squared divided by 2 pi. And it doesn't matter if you do it in the time or frequency domains, the energy is the same. And you can demonstrate that, you can prove it fairly easily. So if we say that a signal x of t, we can find its energy by integrating x squared, and you can represent x of t. So let's say x of t times x of t is x of t squared. So that is the first one. The second one we can write as an inverse Fourier transform. Right? So this is the inverse Fourier transform of x of omega. So that's a strange way of finding x of t, but because we're trying to introduce omega, it does make sense that we do it this way. So if you take the constant out and you rearrange the order of your integrations, if you bring this next to that, that gives you something that looks very much like a Fourier transform. So in the end, you can take your spectrum, you can square it, and with the inclusion of that factor there, you end up with the same energy. So the energy is the same in both domains. That's basically what Parseval is showing us. And we can prove this and we can verify it for individual signals. There's plenty of examples of this in the problem sheet this week. So a few more things to cover, and we will have finished looking at the properties of the Fourier transform. So, for example, and this is a good example, it shows you how useful Parseval's theorem is. So if you had a signal in the time domain, nice simple signal like this, so it's a rectangular function, okay? It's got an amplitude of 1 and a pulse width of 2. And the question is, well, we're told that this has a spectrum that looks like that. And the question is, what is the energy of that signal? And the answer is, well, the energy of this is equal to the energy of that. Of that. So the energy is the same. The energy is the same whether you look in the time domain or the frequency domain. The final property to look at is the convolution theorem. The convolution theorem, we introduced this in lecture 4 at the very end, and I said that that was homework for you to do. And I said that if you take two signals and you carry out a convolution in the time domain, then the Fourier transform, or the spectrum of that convolution, will be the product of the two spectra. And the opposite of that is also true. That if you take two signals in the time domain and you multiply them, then the spectrum of that, the Fourier transform of that, will be the convolution of the two spectra. And there's a factor of 2 pi there. So the spectrum of the convolution of two signals in the time domain is equal to the product of the spectra in the frequency domains, and vice versa. And this is really helpful. It means we can avoid carrying out this cumbersome, this tedious, this annoying convolution in the frequency and time domains simply by doing it as a multiplication in the other domain. So instead of carrying out a convolution in the time domain, we can do a multiplication in the frequency domain to avoid it. And instead of convolving in the frequency domain, we can simply multiply in the time domain to avoid it. So it's a really handy theorem to have. And there's a nice little video where I actually prove this. You can watch this, or I can write it out for you right now if you like. So what we're saying is, if you have two signals f of t convolved with g of t in the frequency domain, in the time domain, then in the frequency domain that should give you the product of f of omega times g of omega. So this is the thing I asked you to do for homework, and you can look it up in any textbook, or you can watch this video here, or I'll try to go through it now. So instead of writing that, I will write this as a Fourier transform. That allows me to say that it's equal. Because in order to say something is equal, it has to be in the same domain. So here we have frequency, here we have frequency, and because we have Fourier transform, here we have frequency too. So what I'm trying to prove is this. Okay, so let's remind ourselves, what's the convolution integral? So a convolution integration is simply an integral from minus infinity to t f of tau times g of t minus tau d tau. And even though we're integrating from minus infinity to t can take any value, so I'll integrate from minus infinity to infinity. Now what you can do is now have a change of variable. and replace, you can say let u equals t minus tau, and then t can then be written as u plus tau. And now if we remember that the Fourier transform is simply an integral from minus infinity to infinity multiplied by e to the minus I omega t, we can now rearrange these integrals. I can replace this t here with u plus tau, and that allows me to say, well, this is a multiplication. I'll leave out the limits and say this is f of tau e to the minus I omega tau d tau times the integral of g of u e to the minus I omega u du. Now if you look carefully, what we have is the product of two integrals, each of which is a Fourier transform. So that looks like a Fourier transform, and that looks like a Fourier transform. Just look at that. So it's clear that we have f of omega here, and we have g of omega here. So we've essentially demonstrated that the Fourier transform of a convolution can be rewritten as a product of two Fourier transforms. And I think I've done a slightly better job of clarifying that in my YouTube there. So that was the final property that I wanted to look at. And this is the summary of the properties we've done today. So this is the convolution property, or the convolution theorem. This is Parseval's theorem that came before that. We've looked at frequency shifting, time shifting, scaling. Remember, multiplication of the independent variable by a. Linearity, where we add signals in the time domain and we look at the effect on the spectra. And duality, where we said that if f and g are f of t and f of omega are a pair, then the same should be true with the minus sign and a 2 pi factor in the frequency domain. So these are the 5 properties of the Fourier transform plus these two bonus. There are other properties. There's, for example, the differentiation property that we haven't looked at here, but I've mentioned the 5 most important properties plus the Parseval's theorem and convolution theorem, because it makes dealing with the Fourier transform much easier. So it might look like there's a lot to take in here, but these, once you've used them a few times, you'll see that they are actually handy tools that make answering difficult questions actually much easier. So do take some time to go through problem sheet 5 and look through. I've got a few dozen pencasts with very useful solutions and working out to prepare you for the class test, and hopefully you'll find the class test quite easy. And once we're past week 6, hopefully the rest of the module is all downhill. So really, I appreciate this might look quite a lot, but this is as difficult and as complex as it gets. The module gets significantly easier after this. Okay, so just a quick reminder of where we are. So we've just finished that. that, if you like, is the end of the frequency analysis or the frequency domain part of this module. We have one more lecture next week where we'll be looking at signals, and then everything else is systems. So from lecture 6 onwards, we're looking at systems. From lecture 1 to lecture 6, we were looking at signals. So just remember that there's one more test. So the next test, test 3, we'll look at lectures 4 and 5, and that's scheduled for the 16th of November. Then the following test will be the 30th of November, and that'll look at lectures 6 and 7. Okay, so that's all I have for today. Good luck with your practice test and with your test, and I look forward to meeting you at our next problem class.